Lecture number 10, some hydration problems. Problem number 8.52. A piston and cylinder have got 2 kg of water at 1000 kilopascal and 250 degrees centigrade, which is now cooled with a constant loading on a piston. This isobaric process and when the water has reached a state of saturated liquid. Find the work done, the heat transfer, and this sketch the process on a PV and TS diagram. So just a very simple problem in which like we have got the initial condition of water at 1 megapascal and 250 degrees centigrade. The water is cooled at constant pressure until it reaches the saturated liquid line. During this process, when it is isobaric process, we have to find the work done, the heat transfer during the process from cooling down from 250 degrees centigrade towards the saturated liquid line, and obviously we have to sketch on the PV diagram. So the first thing like we have to check like where actually the 1 megapascal and 250 degrees centigrade lie. So for that purpose we have to check the steam table. So let's go to the steam table. So at the steam table, if I'm looking at the saturated steam table, so this is my saturated pressure entry obviously. So this is my saturated stream table at 1000 degree sorry 1000 kilopascal, and the saturated temperature is 179.91. So obviously at 250 degrees centigrade the water is superheated as our temperature is higher than 179.9. So let's move towards the superheated region. At superheated region, we have to check the uh, at 1000 kilopascal, which is over somewhere here, and 250 degrees centigrade. At 250 degrees centigrade, this is over here. We have to check the condition, or we have to check different properties, and that properties are like internal. So let me check over here. It is the first thing like volume, internal energy, enthalpy, and entropy. So we have got the volume, internal energy, enthalpy, and entropy over here. So these are our value of volume, internal energy, and enthalpy and entropy. We'll come later on for this one. So, so at state one, we have got the volume, which is this one from the steam table. We have got the entropy from the steam table, which is this one, and we have got the internal energy from steam table, which is this one, 7909.91. Let me check it again. These values, yes, we have got to 0.23268 to 2709.91 internal energy, and obviously the entropy as well, and enthalpy. So coming back, so now it is cooled with a constant loading on a piston. So the process would be isobaric, and then the water should reach the saturated line. So if I'm drawing on a PV diagram, so the condition one is superheated. So at state one, I have got 1 megapascal but superheated. Then it will be on a constant pressure line, it will be cooled down to a saturated liquid line. So my state 2 is at the saturated liquid line. So going back to the steam table, but now at the saturated steam table, I have to find the volume V2, the entropy S2, and internal energy U2. But that is actually my the saturated liquid enthalpy, saturated liquid volume, saturated liquid volume, saturated liquid um, entropy, and obviously saturated liquid internal energy. So going towards that one, you have to go back to the saturated steam table and finding the saturated liquid. We do not need the enthalpy anyway. So we have to find the saturated liquid entropy over here. Obviously, there's another steam table for the other values. this one, sorry, kPa 179, we have got saturated liquid volume, we have got saturated liquid internal energy over here, and we have got on the other page we have got the saturated liquid enthalpy if we need it, and we have got the saturated liquid uh, entropy. So 2.1386, and the volumes are like 0.001127, and obviously the internal energy is 7. So going back to the question again, so say like we have got the from the at state 2 we have got the volume v2 which is 0.001127, and entropy is this much, and the internal energy 761.67 as we have checked. So that's again a simple problem then. So once we have got these values, so the work done in an isobaric process W from state 1 to 2 would be equal to the M if we have got it, pressure into V2 minus V1. So we have already got the pressure, which is 1000 kilopascal. We have already got the volume V2 from this saturated steam table, and we have got already got the volume V1, which was the from the superheated table. Just putting the value, and you will get the answer like minus 463.1 kilojoule. We have got the minus sign because it is actually being compressed, or we are actually going from the hotter side or the high volume side to a lower volume side. From the energy equation, we can find the heat transfer, and the heat transfer is actually change in internal energy plus work done. We already got the value of internal energy. We have already got the work done. We already calculated the work done right now. So mass multiplied by the internal energy u2 minus u1 minus the work done, which we have got it. So we have got the heat transfer, which is 4359.6 kilojoule, and that's again minus because it is being cooled down. Now moving towards the next problem, problem number 8.53. 1 kg of water at 300 degrees centigrade. Expand against a piston in a cylinder until it reached the ambient pressure of 100 kPa, at which point the water has got the quality of 90.2%. It may be assumed like the expansion is reversible and adiabatic. What was the initial pressure in the cylinder, and how much work is done by the water? So this is the condition in which we have got initially we have got only the temperature known, and at the second state we have got the pressure known and also the quality known. So and obviously we have to just start from the state number 2. So what we need to find out is like the work done on the by the water in the and the initial pressure. So first thing, like let's check the from the initial condition, or sorry from the final condition. Let's find the entropy, internal energy, and so on. We will check the later on like what we need to find out. So at pressure P2, sorry, pressure P2, which is 100 kilopascal, just go to the steam table and find the value of Vf and Vfg. So once we have got the value of Vf and Vfg actually, so we will find the value of no sorry no, what I'm we have already got the volume, so we do not need to find the value of volume Vf and Vfg, sorry for that. Just find the value of Sf and Sfg. So from that one we can find the value of S2. So S2 would be equal to Sf plus X2 SFG at 100 kPa, and obviously later on you can find the value of U2, which is actually UF plus X2 UFG. So going to the steam table, saturated steam table, at pressure of 100 kPa, find the value of SF and SFG from here, and obviously it's VF and VFG. Sorry, it's VF over here, VFG over here. So you can find the VFG at 100 kPa. We can find the value of VF and VFG. Putting this value in here, you can find the entropy, which is entropy S2, and the internal energy, which is U2. Now, the required is like what would be the initial pressure. So initial is actually we have got only one condition known, which is 300 degrees centigrade. So how would we find the second condition at the state number one? So it's a like the process is reversible and adiabatic. So that means like the process is isentropic. So isentropic mean like we have got the entropy S2, which would be equal to S1. So going back, like we have already defined the entropy, which is 6.7658, and that entropy is equal to S1. So at condition 1, now we have got, sorry, at state 1, now we have got two conditions. The temperature, which is 300 degrees centigrade, and the entropy, which is actually equal to 6.7658, which is equal to already equal to S2 now. So at 300 degrees centigrade, entropy S2, S1. So we have to just go back to the steam table and match these two values. So going towards this saturated steam table, let's check the value of S over here, which is 6.7658. Going to the steam table, checking the value at 300 degrees centigrade. So at 300 degrees centigrade, if I would check the value of Sg, which is over here, which is saturated vapor, so which is 5.7436. So the value of Sg, the S1, which is 6.76 something. So my Sg is my value of entropy is greater than the value of Sg over here. So what I'm saying like the my value is greater than Sg, so I'm in a superheated region now. So going to a superheated region or going to a superheated table, looking for the 300 degrees centigrade and this entropy wherever it matches, so we will check the that entropy. So the superheated entropy at 300 degrees centigrade, I'm looking at the entropy value, which is somewhere near to 6.7636 something. uh, Moving down, actually the entropy would be increasing, I mean like increasing the pressure, the entropy is decreasing. So we are increasing again, so 300 is somewhere, we have got this one. So at 300, 1200 kPa, no, we do not have it. And let's check over here at 300 degrees centigrade and 2000 kilopascal, which is 2 megapascal. I have got the entropy, which seem exactly the entropy, which is actually matching with the value which I've got. So at 300 degrees 300 degrees centigrade, I've got the entropy, which is 6.7663. So let's check our value of S1. So we have got 6.7658, and the value which was written over there is 6.7663. So almost near to the this value. So I'm saying like it will be somewhere roughly equal to 2000 kilopascal. So my pressure, initial pressure, which actually I've got, is 2000 kilopascal. Yes, you can say like we need to interpolate a value a little bit, but that would be too tedious job. So just I would just leave this value, and which is actually equal to pressure is 2000 kilopascal, and obviously at that 2000 kilopascal pressure, we have to check the internal energy as well, and that internal energy is equal to 2776.56 now. So I've got the internal energy, I've got the entropy. Now the work done from one state 1 to 2 would be equal to the change in the internal energy only, as the process is adiabatic. So multiplying the change in internal energy with the mass, we can get the value of 471.2 kilojoule. Check the PV and the TS diagram. Problem number 8.57. A closed tank with a volume of 10 liter containing 5 kg of water initially at 25 degrees centigrade is heated to 175 degrees centigrade by a heat pump that is receiving heat from the surrounding at 25 degrees centigrade. Assume the process is reversible, find the heat transfer to the water and the change in entropy. Same thing, like we have got the process which is reversible now. Writing down the energy equation and obviously the entropy for the reversible process. So finding the initial state, it is a closed tank with a volume of 10 liter. 1 cubic meter is equal to 1000 liters. So you can do your conversion later on. So at a so it's a closed container. So the process work done would be equal to 0 in it. If I'm looking at this equation. So initial volume V1 by initial volume will be volume of the tank divided by the mass contained in it. So it will come up as 0.002 uh, cubic meter per kg. X1, if I'm looking at the value of the quality, so it will be from the steam table at 25 degrees centigrade. We have to check the value of Vf and Vfg and finding the value and then putting the value V1 would be equal to Vf plus X1 Vfg at 25 degrees centigrade. Let me check the steam table now. So at 25 degrees centigrade, the value of Vf and Vfg would be here. So we have got 0.001003 and 433583. So putting this value in here, we have got the value of x, which is 0.000023. Now putting this value of x to, to find out the value of u1, which is u1 would be equal to uf plus ufg at 25 degrees centigrade. So finding the value of u at 25 degrees centigrade, just go back to the steam table and you will find out the value of u, f and ufg over here. So 104.86 and 2304.90. Going back again, so we have got 104.86 and 2309.49 for ufg. We have got u1 now. Similarly, we can actually say have the same exercise for the value of S1. So S1 would be equal to SF plus X, sorry, that is X SFG at 25 degrees centigrade. So you can just check the value later on in the steam table and you will find out the value of S1. Now at state 2, it's a like now it is receiving heat, and that mean like it will be the temperature will go up to 175 degrees centigrade by heat pump that receive heat from the surrounding at 25 degrees centigrade. So going towards the temperature T2 now, the volume V2 would be equal to V1. So from the same thing, like going towards the temperature T2, so checking the volume at 175 degrees centigrade and with the volume which is equal to 0.002, Let me check like whether it will lie inside the vapor dome or not. So we have got the volume which is equal to at 175 degrees centigrade. We have got the volume of Vg at 0.21668. Our own volume is 0.002. So that means like we are still inside the vapor dome. So if we are still inside the vapor dome, so we will be still using the value of sorry these kind of a formula. That means like we need to find out x2. X2 would be equal to x2 would be find out using the volume formula. V2 would be equal to Vf plus x2 Vfg at 175 degrees centigrade. So checking at 175 degrees centigrade the value of Vf and Vfg, so we can find the value of x2, putting these value, and we can find the value of x2. And similarly we can find the value of u2 and s2 over here. So finding the value of u2 and finding the value of s2, now putting that value in the equation as the work done was equal to 0, so the heat transfer would be equal to change in the internal energy only, and the change in entropy would be equal to s2 minus s1. Just you need to put up the value and getting the answer. Yes, let me remind you, like if you do not have got the steam table, or if you have got the steam table, we do not have got the internal energy value. So internal energy can be find out using the enthalpy formula, which is U plus PV, and the internal energy can be found out by using H minus PV over here. So you can use the formula of H and PV.